Hey,
Okay.
so I may start, Zihua.
Yeah, let me introduce you first.
Oh,
Okay.
okay. Oh,
Okay. Good afternoon, everyone. And we welcome to our December SLDS webinar. It is an honor to have Dr. Harrison Zhou as our webinar speaker today. Harrison is Henry Ford II Professor of Statistics and Data Science at Yale University. He earned Ph.D. in mathematics from Cornell in 2004. Um, a leading scholar in the statistical decision theory, Harrison is known for his work on the fundamental limits of statistical estimation. He also made a significant contribution in a wide range of areas, including large covariance matrix estimation, graphical models, Bayesian nonparametric statistical network analysis, and analysis of iterative algorithms. His research has been acknowledged by NSF Career Award, the another Young Scholar Award, IMS Medallion Lecture, and he is a member of the Connecticut Academy of Science and Engineering. He currently serves as an editor-in-chief of the Annals of Statistics. During his tenure as department chair at Yale, he played a pivotal role in transforming the Department of Statistics into a full-fledged data science department. And without further ado, let's welcome Professor Zhou.
thank you, Zihua, and for your very kind invitation. Uh, I'm very pleased to have the opportunity to speak in this seminar. You see my background. My background is a very ugly building, and that's where the Department of Statistics and Data Science at Yale is located, and it's on the Science Hill. And on the Science Hill, is the tallest building is this building, and so at Yale, the Department of Statistics and Data Science is looking down all other disciplines. So okay, this the topic over here is on sampling, a new way to do sampling, and it's only new to me, and the idea has been there for a long time in both machine learning and statistics. The idea got very popular in the past few years due to the development of generative AI. And the idea is very strange, and at least very strange to statisticians. And so that's why I decided to work on it. And from a statistical perspective, it's really a crazy approach. So this is a joint work with three students, and actually, oh, with three students, and actually, and Super is my academic grandson, and he's now a winner, a postdoc at MIT, and Zhou Dou and just graduate early this year, and part of this talk was his job talk, and at OpenAI, and Zhou Xu, and you see the names are very nearly identical. And for someone from the south of China, that's the most challenging part in our project, joint project, and to distinguish these two names. And Zhou is heading to hedge fund, unfortunately. Or fortunately, if one day he's giving back to higher education, I guess these days we need more money than ever. The sampling approach is called diffusion, and I'll first give a very brief introduction to the diffusion models to those who have never heard of it. And to implement the diffusion model or the sampling approach, we need to do something called a score matching or score estimation. That's a very critical step. And later, and we are going to evaluate the new sampling approach and by Watson distance and total variance distance. And that's a distance we use to measure two distributions. And Watson distance is a fascinating distance, and which is connected to a concept these days very active research area and optimal transport. So we have seen a tremendous success of diffusion models to generate a new image or new video and from $3 and stable diffusion. I guess in academia, this is better known, and a diffusion approach was playing a key role in AlphaFold 3. So, okay, what's a diffusion approach? Again, it's a sampling approach. And suppose we have a lot of dark images, let's say 1 million dark images, and you hope to generate a few more dark images. And what to do? To a classical statistician, that means, oh, we need to estimate the distribution of the dark images, which is very high dimensional. And the diffusion approach is an indirect way to do sampling. And so what they are doing is this, it's based on an imaginative and mental exercise. So what they did is this, let's say, okay, suppose I have a dark image, and I add noise to dark image, it's becoming blurry. And if I add a lot of noise and to the image, it's becoming, basically like white noise, right? Suppose you have a dark image, you add noise, become blurry, and more noise, more blurry, then eventually it's like a white noise. And then people ask the question, can we reverse the process? And can we start and form a white noise to eventually generate a beautiful picture of dark? And so that's the question they ask, and it turns out that's possible. And what you need to do is to using some kind of a classical stochastic process idea. And so and what I was talking about, you could formulate it. What I was talking about is more general, right? Description, what people would do, and you can formulate it rigorously, and by using stochastic PD. And stochastic differential equation is this. What you have is, and let's say you have a drift function 0, and you have g over here is equal to 1, and originally you start with a dark, let's say x0. Then dWt over here is Wiener process. It's just adding Gaussian, independent Gaussian noise, actually. And it sounds, complicated. Just adding independent Gaussian noise. And so the reverse process is running a reverse SD. That's all we are doing over here. Reverse SD here. So let's say that's the reverse SD and is completely determined by something which is called a score function. And the score function, and looks complicated. It's a gradient of something. So that score function must be related to the distribution of my dark images, right? If it's not, that means something is wrong. And how can I generate a beautiful dark image from white noise, right? And it must the score must be somewhat related to distribution. Otherwise, it's not making any sense. And there's an alternative way to generate is to run an ODE over here, and instead of SD. So the ODE, of course, for ODE is a deterministic process, and if you have one input and then you have one output, and which is different from SD. You have one input, you might have several output, and it turns out, and their outputs have exactly the same distribution, and the same distribution as the distribution of original dark images. Is that clear? And this is just the very basic idea of the diffusion model, and it's based on again an imaginary mental exercise. Assuming you just add noise, and then can you go backward? So, and to a typical statistician, you will say, no, Harry, this is a crazy approach. How this approach would ever work? What you are doing is just you're adding noise to your data. And it turns out, now this is the kind of one of the most popular model in generative AI. So, and to understand this sampling approach, and we use the simplest model, and we use the simplest model in the simplest setting, and just to see whether the approach is as good as any other approach, and we have proposed in statistics. So, and this is the simplest case. Eventually, of course, we have to go beyond this case. And suppose you have a one-dimensional sampling problem, okay? And you have n data points with the density f, and we are asked to generate a few more a sample, and with the density f or approximate f. So and many of us would come up with all kinds of approach and based on your experience and in statistics. But today we try to do it by using the diffusion approach. So to apply diffusion approach, what does that mean? That means we are going to run this reverse SDE SDE and to generate new sample and from something like white noise. So and to implement that algorithm in one-dimensional case, and what we need is to get what we need and is to get the density at time t. So what's the density at time t? And this is the density of original data plus or a normal zero t noise. And we have Wiener process, and at time t you have normal zero t noise. And so and you have sum of two random variable, and what's the density? The density we denote p of xt. So and for that density, if you take a log, you take a derivative, and with respect to x, then you get something called s of xt, and that s of xt is called score. And if you have taken theory of statistics in graduate school and in the textbook, usually we use m instead of p, and m means the marginal density. And if you take the partial derivative of log m, what do you get? You get something related to posterior mean. Actually, the reverse process is doing the posterior mean. So, and let's say, okay, well, you have the score, then you could run the reverse SD. So, okay, and if you do that to generate new sample, and this algorithm would have at least two sources of error, and one source of error is this. And what's the initial value you need to put? The initial value you put over here, is supposed to be original data plus normal zero t noise. And but since you do not have the original density, you do not have the original data. What you do is you may just plug in a normal zero t noise, you want noise to start. So you run the reverse SD, and then the score over here is related to the density f, right? And the density f is unknown, and that means you have to estimate it. If you estimate it, and then that is a source of error, and that source of error, and that will be a score estimation error. So there are two sources of error, and one is the initialization, and the other one is the score. It turns out for the initialization, the error can be well controlled, and if your t is very big, so let's kind of imagine that you have your data. If you add a huge noise, and then it's just noise, right? And then what's the difference of these two distribution? You can well control it. It's like 1 over t. And when t is like as big as n, you get 1 over n error. And in statistics, usually you cannot get an error better than 1 over n. So that means the main source, if you pick your t is really big, the main source of error would be the score estimation error. You estimate s by s hat. Is that clear? Okay, and suppose you have a good score estimator, and this is my true score, and this is my estimate of score. And suppose you could estimate very well, and it turns out you have a very good control over the sampling error. If the sampling error has such an upper bound, and this upper bound and is from a paper by my colleague Chui and his co-authors. So what does that mean? That means if you could estimate the score consistently and you could sample consistently. And this upper bound may appear to be very strange to you, and it turns out it's a very simple upper bound. And what you need to bound is the difference of two marginal at time zero. But since my S hat could be very strange, my sample may not really have an explicit form, and it's very hard to figure out what the density is like. You do not really know how to calculate total variation distance. And what they did is this. They did is, okay, I supposed to calculate the difference of two marginal, but what I'm doing is I compare the difference of two whole processes. And look at the difference of two whole processes, and then they apply a so-called Gaussian formula. And because for two whole processes, and there are some simple ways to calculate the difference of two whole processes. It's kind of very strange upper bound, and somehow you may not even believe this upper bound. You said, okay, Harry, how could that ever be helpful? At least that's kind of the one of the most popular upper bound people use to check the sampling error for the diffusion approach. So again, if you have a consistent estimation of the score, you have a consistent sampling. So and in this talk, we are going to think about it more ambitiously. Suppose you have a way to estimate score optimally, and in statistics, we often show this kind of result. You could do some kind of score, some kind of function estimation in an optimal way. And then the question is, can we sample optimally? So if we actually score optimally, and do we sample optimally? And then we'll talk about score optimally. Let estimate score optimally. That means you need to have a loss. Then what loss you should use? And inspired by the upper bound over here, and we use this loss. And this loss may or may not be useful, but that's kind of a way. And the upper bound for my colleague at least inspire us to consider this kind of loss. Is that clear? Again, I will think about the simplest function class to test the diffusion approach. Of course, eventually we have to go beyond this, otherwise it's not interesting. And we think about, we assume that our function is in a hollow ball, and for hollow ball, we know nearly everything about it. And people have done a lot of research in the past 40 or 50 years, or even longer, and 60 or 70 years, depending on how do you see it. And so, for this function class, and if and you may show that under the total variation distance, and this is the error you get, and n to the power minus 2 alpha divided by 2 alpha plus d, and this is the dimension. And if we use total variation distance or L2 distance to measure the error, and in this talk, I will talk about what's the distance as well. And this is a distance. A lot of people may not know it, but it turns out it can be helpful and could be very helpful, and for us to understand diffusion approach. So the arrow over here, may look very strange to some of you if you never heard of what's the distance. And I guess something is good to observe is, the arrow, this arrow is far smaller than this arrow. And when d is equal to 1, and the arrow over here is parametric, and the arrow over here, of course, is not as good as parametric for non-parametric estimation. What's going on? Oh, okay. So, okay, to implement this algorithm, and we have to estimate score, and we call it a score matching. And so that means we need to come up with ways to estimate the score. So, and one way to estimate score is very natural way is, okay, we have come up with all kinds of approach to estimate the density. And suppose you have n data points with a density f, and with the density f, we have come up all kinds of ways to estimate density. We have used Cornell, we have used wavelet, we have using Fourier basis, we have using Splan, and so on and so on, local polynomial. So, okay, what's my score? My score has two parts, and the denominator is the density at time t. Again, is f convolved with phi t, and f is the density of the original data. And what's the numerator? And the numerator is the derivative of the density. So keep in mind, okay, this is what we had before, and because we are taking the derivative of log function. For the log function, what you get is p prime divided by p. So, okay, and how do you estimate the denominator? And one way to do it is I just plug in, my Cornell or whatever density estimator. And what about the numerator? Numerator, I just plug in because it's a derivative of the denominator, and I just plug in the derivative of my estimator for the density. And then you look at, oh, Harry, there are some other strange terms over here. What are they? And these are, you could just ignore these. They are there due to some kind of boundary effect. And because I assume my function is bounded. So, okay, if you plug in your favorite estimator, and I expect you will get this kind of estimation accuracy for your score estimation. And the estimation accuracy is this, is you get some rate over here. So this rate must be familiar to some of you. This rate you get is the estimation accuracy of the derivative of density, and the density has the smoothest alpha. Then the second part, you may just ignore it, is due to some kind of boundary effect. So, and why does this guy appear in my estimation accuracy? Because I'm estimating f prime over here. That's it. That's the reason. So, and this is the starting point. Just okay. And as a statistician, we have come up with all kinds of ways to estimate density. And one way to do it is just plug in, right? But we all know that plug-in estimator is not always the best. It's often not optimal. And when, as an example, if my t is equal to 1, so what's phi t over here? Phi t is just the density of normal 0, 1. And normal 0, 1 is infinitely differentiable. Then convolve with f is also infinitely differentiable. If the denominator is infinitely differentiable, if the numerator is infinitely differentiable, what does that mean? That means you should be able to estimate the score in a nearly parametric rate when t is like 1, right? So that means this upper bound over here could be horrible. So that means we may consider some other estimators as well, and this is a good candidate to think about. But apparently, sometimes it may not be optimal, and so we should think about some other estimators as well. So another estimator is the estimator from my colleague Yihong Wu and his authors. So again, okay, what's the score? And the score has two parts, and you have the denominator, and you have numerator. And the numerator is the derivative of the denominator. And now I'm taking derivative with respect to phi instead of f now. So okay, if I take derivative with respect to phi, and you take derivative for the phi function, and then this is the denominator. So okay, how do we estimate the score? And a simple way to estimate is this. And so what's my phi t over here? My phi t over here. What's my denominator over here? My denominator here can be seen as the population mean of phi t of x minus mu, and population mean and with the density f of mu. So, and how do you estimate the population mean? You estimate population mean by sum of mean, and that's what I was teaching in my basic probability class at Yale. And I was teaching a basic probability class with more than 300 students. And okay, how do I estimate population mean with sum of mean? And similarly, for the numerator, you could also estimate the population mean by the sum of mean. And we observe a sample and n data points mu1 to mu(n) with the density f. So okay, and now you would like to figure out what's the estimation accuracy if I use this unbiased estimator, and proposed by my colleague Yihong Wu. And so all you need to do is, okay, is the variance of these two terms, right? You do not care about the bias because it's unbiased. So if you know how to calculate the variance, and basically you're done. And you plug in, and then you get this error rate. And if you use an unbiased estimator, then you get an error rate 1 over nt to the power 3 over 2. When t is equal to 1, what's the error rate? When t is equal to 1, you get 1 over n. And when t is far bigger than 1, what does that mean? Then you get an error rate even faster than 1 over n. So this is an unbiased estimator. And so, and now I have a quiz. I have a quiz for many of you and who are here. And I guess in my probability class I have to give quiz, and otherwise they will not go to class. And so, and if the quiz is this: if for all time t, if I estimate my score in this way, and then I plug in to my reverse SLDS to generate a new sample, and what kind of sample do we get? So suppose, okay, for all time t, and my estimator is this, right, to estimate score, and I plug into my reverse SLDS. Then the question is, and what kind of sample do we get? And it turns out what we get is just a resampling of the original data. You're not generating anything new. It's not interesting at all. And in statistics, what we call it overfitting problem. So, and since this is an estimator, and from my colleague Yihong Wu, and who is more capable than I am, and I was assuming, okay, I cannot do better than his approach, but as a decision theorist, and I would hope for when t is large, and this is the best we could do, but for a long time we tried to prove that's the best we could do, but we failed. So that means we may have to come up with some other approach to estimate the score as well. So this is a new way to estimate the score, and this way, again, if you remind you, and the score is has two parts, a denominator and numerator, and the numerator is a derivative of the denominator, and this form is exactly the same form we had before, but we are doing something different. And if you look at x minus mu over t over here, and in the numerator, and I would split x minus mu over t to x over t minus mu over t. Okay, I'm splitting x minus mu over t to x over t minus mu over t. If I do that, and then I have a different way to write the numerator. So the first term over here is minus x over t times p of xt. So what's p of xt? That's exactly the denominator over here. So what does that mean? That means if I divide it by the denominator, then I get minus x over t. This is a quantity I do not need to estimate. Is that right? Because it's known. So the only quantity we need to estimate is this guy. So again, how do we estimate this guy? We may estimate this guy again by the population mean by summer mean. Okay. Again, if you know how to calculate the variance of this guy, then you know what kind of upper bound you would get for the estimation accuracy. It turns out you get an upper bound 1 over t squared. And when t is far bigger, than 1, and this is smaller than the previous bound we had. Say, when t is equal to n, you get 1 over n cubed over here, right? And for the previous bound, when t is equal to n, you get 1 over n to the power 2.5. So, okay. And if we put all three estimators together, and then this is what we have. And we put three estimators together, then this is what we have. And when t is large, and the last estimator was the best. And this is the smallest error, and this error is far smaller than 1 over when t is far bigger than 1. When t is small, let's say t is close to 0, and this guy is the smallest, and this guy would be horrible, okay? And when t is small, and when t is somewhat in between, and then the estimator from my colleague Yihong Wu would be the best. And so, and if you have energy to look at the phase transition and between those terms over here, and the first phase transition over here would happen at t equal to 1. And that's the first transition over here. And the second phase transition and would happen over here. And this one would be related to kernel smoothing. And for some of you who have done kernel smoothing before. And so, and then, okay, so we have the upper bound. But as a decision theorist, and I will ask the question, is that the best we could do, right? When t large, you use the one bias estimator. When t is small, you use a plugin. When t is somewhat in between, you use my colleague Yihong Wu's estimator. And then the question is, can we find an estimator to beat those estimators? Is that possible, right? And we may ask this question as a decision theorist. Yes, there's a question?
There is a question from the audience.
Yeah.
Quick question to confirm, does the upper bound on page 14 also hold for t greater than 1?
Oh, yes. That holds for t greater than 1 as well. And I put in t less than or equal to 1 just because and when t is more than 1, this rate is not optimal. That's why I put in t less than or equal to 1 here. That's a very good question. That means they paid attention to my talk. I am grateful. Thank you. So there's a again, this, if we put all three together, and then we have estimator and perform differently at a different range, and sometimes one is the best and sometimes the other one is the best. And then again, I was asking is, can we beat this approach? And suppose on Zhihua, okay, and look at this slide. Hey, Harry, I have another approach. I can beat it. And your approach, right? That's possible. Why not? And yeah, younger and more energetic. And so, and then as a decision theorist, and we would prove and whether we could improve the upper bound by construing some lower bound. And this part could be very hard for many of us to understand. And basically what we are doing over here is this. We try to figure out the intrinsic dimension of the problem. and the intrinsic dimension would be denoted by some by something called m here. So that's the intrinsic dimension. And after you construct the intrinsic dimension, and then what we do is this: we construct a very small set of functions, and actually they are discrete, and that set is a small subset of the whole function space, and but it would capture the difficulty of the problem. And so, and for that, because it's discrete, and we could do all kinds of fancy calculations, and then eventually we show that, and because we show that for this small set, and the best estimation accuracy would be the accuracy we talked about before, and that's the proof. The proof is, let's figure out the intrinsic dimension, and then we give a proof, and by constructing a small prime space. And the proof, the analysis is kind of cute, and it's one of the, I feel, one of the few times in my life, and heat equation is kind of helpful and to prove something. And when I was a graduate student, I learned admissibility, and I was amazed by Larry Brown's paper, and heat equation was used to prove admissibility there. And so okay, and this and a brief comment over here is this: we try to figure out an intrinsic dimension. Then we are trying to construct something very simple so that we can do calculation, and then we show that it turns out, at every time t, I cannot beat the estimators we proposed. When t is very small, we cannot beat the plugin estimator. When t is very big, we cannot beat the second unbiased estimator. And when t is somewhere in between, we cannot beat the unbiased estimator proposed by my colleague Yihong Wu and his co-authors. So I guess again, most people will not really care about the lower bound. I guess the upper bound is more interesting. Would give you some sort of procedure and to implement. So and here I have some comments to make, and brief comments which can be helpful to us. And one is I get results for all t, including t very close to 0. And this is very different from what we have seen in literature. They often have an early stop somewhere, and one reason to have early stop is when t is very small, and the estimate for score could be horrible in practice. And of course, another advantage to do early stop is a computation reason. And another thing I would like to make is this: in literature, people often assume their score has kind of smoothness, and like Holder smoothness or Lipschitz condition, and then they may get the same accuracy at all time t for the score estimation. And this is very different from what we have over here. Well, what we have over here is at different time t, you should expect different accuracy, and which is very crucial and to understand the score. And on the implementation side, this is also very important. And we should use a different precision at different time t. Otherwise, we may be in trouble. And another thing is, the result holds for all smoothness alpha. And in literature, and at least in statistical literature, and you often see that people may assume alpha equal to 1, or assume alpha equal to 2, or assume alpha between 1 and 2, and they may see this kind of result. But in this talk, you see that, and this is true for all alpha more than 0. You do not have to assume the diffusion is only works for a limited range of smoothness. That's not true, and it could work for all range of alpha. And so, and now, okay, and suppose, okay, you apply this score estimator to your diffusion approach, and then you go to sampling, and then you will ask, okay, how well we are doing in the sampling. So one way to measure the sampling is to use total variation distance and total variation distance. And okay, how do you bound the sampling error and the total variation distance? And again, one way to do it is to use the upper bound of my colleague Chui and his co-authors. And so what's that upper bound? That upper bound is this. You just sum all together of the error at a different range of t. So and this is a t large, and this is t small, and this is t somewhat in between. And if I put sum all together, and I was amazed by the upper bound, and the upper bound is exactly the upper bound we would get by any statistical approach. And so I was assuming, okay, diffusion could be good, but the upper bound could be horrible, right? Because you're bound to marginal by the difference of two marginal, by the difference of two whole process. That could be horrible upper bound, but somehow it works over here. Then I look at this upper bound very carefully, and what I found is this: it turns out the dominating term would be the term with very small t. That's kind of part of the reason. That's part of the reason it works. And because over here that corresponds to an t equals 0 case. That's the original data. So that's a estimation accuracy or sampling accuracy under the total variety distance. Any question? No? Okay. So another distance we use is Watson distance. And to statistician, at least an applied statistician, you say that, oh, Harry, who cares about Watson distance? And they may say, okay, I never heard of it. But actually, Watson distance is can be very useful. And before the diffusion approach, the most popular generative approach to generate image was GAN. And GAN, another word for GAN is generative adversarial neural net. And what people realize, and for GAN is this, and if you use a neural net, use GAN to train your neural net, and GAN is not very stable. And suppose you have 1 million data, then later you have 10,000 or 20,000 more data, and you train the GAN again, you train your model again, and your neural net and weight could be very different. So it's not very stable. If it's not very stable, then you start to question, oh, is my model right? And that's part of the reason, and people switch to diffusion these days. And before they switched to diffusion, there was another GAN approach. It's called Watson's GAN. And Watson's GAN is to use the Watson distance. And the reason they use Watson distance is this. If you use total variation distance, you have your sample, you have total variation distance. Let's say you have a sample and discrete measure. If you change your sample a little bit, and then the total variation distance could go from 0 to 1. But Watson distance would not really change, would change very little. So, because it's more stable. And that's part of the reason, and the Watson GAN was very popular for a while. So what's Watson distance? And Watson distance is a distance to measure two distribution or two density. And I use two density over here. I use 2 pi of dot. Okay, I hope it's okay to you to understand in this way. And the Watson distance is this. Suppose you move this pi of dot on the left to this pi of dot on the right. So when you move the dot and from left to right and to match the shape of the right, and 2 things will be involved. And one thing is the distance you travel, right? If you travel longer distance, that means you are taking more effort. Another thing is the mass of the dot you are traveling. So the distance times the mass is the effort. And the minimum effort or the smartest way to travel to move from one door to pi to the other pi is called Watson distance. So, and the Watson distance and it has been very popular distance in machine learning. And for one-dimensional case, the Watson distance and can be easily calculated, and because we know the optimal way to transport, and the optimal way to transport is to use this. This is called quantile coupling. Again, and I was teaching basic probability, and this is something I was teaching in my class. And suppose you have your data, okay, x0, which is on the left, and has a CDF f. Okay, what's the distribution of f of x0? That's uniform. And then, okay, if you look at G inverse of uniform, what's the distribution of that? And that would be the distribution of x1. So it turns out lattice transformation gives us the optimal transport in this case, in one-dimensional case. And when the dimension is more than one, then the formulation is very much complicated, and then it's becoming harder. So, and one way, and a very popular way in both statistics and machine learning is to bound Watson distance and by a total variation distance. Is to bound Watson distance by total variation distance. If you bound Watson distance by total variation distance, and then what kind of estimation accuracy you would get? The estimation accuracy you would get would be something like this, right? Which is a non-parametric rate. But actually, and for CDF, you could estimate it's a parametric rate, right? And so that means you should be able to estimate the Watson distance with a parametric rate, because you could estimate CDF by parametric rate. And when people talk about the origin of non-parametric estimation, the origin of non-parametric estimation was actually to estimate on CDF in a non-parametric way. Then you get a parametric rate, and which was proposed how many years ago? Maybe 70 or more years ago. So there's and then you would expect the best rate of best estimation accuracy and the Watson distance should be parametric. And then the question is, if you use a diffusion approach, and are you going to get the parametric rate, right? And it turns out if you use some kind of fancy stochastic process approach, you could prove that is true. So, and this slide is complicated. You could ignore it. And the key idea is this. The key idea is, okay, I need to move this dot from one side to the other side. And then I could create a lot of intermediate stops. And between any two stops, I could bound the distance I'm traveling very well. And also I could bound the mass I'm traveling very well. And then if I sum all together, and then I get parametric rate. This is kind of amazing, right? So amazing in this sense, Watson distance, and okay, and we kind of believe, by this argument, it should be parametric. The best rate is parametric, and I would never expect my diffusion approach and would get a parametric rate. Although the diffusion approach has been very successful, very stable, and you may start to get conjecture. Maybe diffusion approach is doing some kind of minimization under the Watson distance implicitly, right? Some people may conjecture that, and so it turns out it can prove that in this case it is minimizing and under the Watson distance and optimally. Any question? No? Okay, I hope I'm not losing all of you. So, and the extension to multivariate case is kind of boring. and you could think about d more than 1 very extended to d more than 1 very easily. And when d is equal to 1, this is exactly what I got before. And of course, there's another term I just ignore it, and for t more than 1, and then if you plug in, and you'll get this rate. When d is equal to 1, you get exactly what you got. And on the Watson distance, and on the Watson distance, when d equal to 1, you get parametric rate. We talk about it. When d more than 1, you get some other rate, and which is better, smaller than the rate under the total variation distance. So, and this is kind of a boring part, a very routine extension. So, but we have some other questions to ask. Other question is, okay, and we have fascinating function class over here, and because we have complicated image, we may have text, and the smoothness class may not be valid anymore, and if we only argue an optimality under the whole smoothness class, and then people will not pay attention to us on the practical side, right? And I believe for any function class, optimal score matching will lead to optimal sampling for any function class under total variation distance. And we haven't succeed proving that, but it's kind of close. And we basically say for any for a certain function class, if we prove the estimation accuracy is something, that's the best you could do. And diffusion approach will do that as well. And if we could estimate score optimally, then you may ask, okay, Harry, how could you estimate score optimally? And a common way in machine learning theory is to do some kind of empirical risk minimization, and you will do that. And you may do that. But an answer to this question is just saying that and diffusion approach is not crazy. And although it appears to be crazy to us as to a statistician, a traditional statistician, and you do some kind of adding noise, you kind of linear do some kind of denoising, but it did not explain the success. And I'm expecting the reason of the success. One main reason of the success is the diffusion approach is doing some sort of implicit localization and to minimize under the one-side distance. And we have already proved it and for the holdable, and I expect some kind of similar results, and it could be true for general function class, but we are still far from that. And so, and one thing I would like to comment over here is this. And suppose, okay, I'm asking you to implement and the diffusion approach and to do sampling. And under the holdable assumption. And for t it's very small, and you may plug in whatever estimator you have. Okay, either kernel, either wavelet, or Fourier, whatever approach, and which is really optimal under total variation distance, but could be horrible under one-side distance. It's possible. But if for t large, if you use our unbiased estimator, for t small, you may use your estimator, which is optimal under total variation, but very bad under one step. It's okay. But for t large, we use our unbiased estimator. And then you put these two together, and then your estimator would be improved to be optimal under the one-side distance. So and this is kind of amazing, right? And it's improving the performance under the one-side distance. And then what kind of theory we should use? And if this is indeed true, maybe we need to change the current objective function, the current loss, and to use a different loss, and so that the procedure will be doing well under the one-side distance. So this is the practical implication. So since we have already talked about one-side distance, and one-side distance is closely related to optimal transfer, and and maybe we could spend a few minutes talking about it. Zihua, is that okay? We spend like 5 minutes. Okay. So an operator transport is uh, uh, is a transport, but it transport optimally. And so as a statistician, you say, okay, as long as you could transport my data, who cares about operator transport, right? And somehow my conversation with people in medical school and some colleagues in single cell, and somehow they are crazy about operator transport. They kind of believe that, and they kind of believe, and in some kind of physical sense, operator transport is a reasonable way to do, and which kind of changed my mind, and so we started to work on operator transport. And this is a joint work with Chang Liu, a professor at UT Austin, and a very smart, brilliant researcher. And I very much enjoy working with him. And two students. So and Chang proposed a transport. It's called rectified flow. So okay, the transport. The record flow is very nice. Suppose you want to find a transport from x0 to x1. What does that mean? You have your sample with a distribution identical to x0, and you have another sample with a distribution identical to x1. And then you hope to find a map and from x0 to x1. What does that mean? And you hope T of x0 would have a distribution identical to x1. So originally, your x0 and x1 could be independent. And then, okay, and how do you find a transport? And he proposed an approach. The approach is you run an ODE. The ODE with the initial value equal to x0. And then with an output, and that output will be something, okay, and that ODE is determined by this kind of velocity. And what's that velocity? Velocity is a conditional expectation of this guy and given this guy. So what you have over here is, as long as you know how to calculate this conditional expectation, then you know how to run this ODE on what kind of velocity at each time t you are going to use. So, and that's a very simple approach. And if you run this ODE, it turns out at time 1, Z1 would have identical distribution as X1. So super nice approach. And if you care about operator transport, and maybe you use a different velocity, and you may project the velocity to a function space. That function space is a function space if a function is a gradient of another function. It's kind of a special function space. And for people in physics, they may care about that. For people who do not care about physics in high school or college, and you may not really know what I'm talking about. And for every function, you could always do a decomposition as a function in the gradient space and also in the complement of gradient space. Let's say there's a famous decomposition of function there. So if you care about operator transport, and you may project your function to a gradient space because the operator transport is a gradient of some function. So okay, and the good thing is this: if you run this ODE, and you could show that originally your x0 and x1 could be independent and they could be far away from each other. And if you run regular flow or C regular flow, and there will be a coupling between x0 and x1, the distance is getting smaller, or transport distance is getting smaller. If we run C regular flow again and again, then eventually, and it will converge to something, and converge to the operator transport. And this is kind of amazing. Amazing in this sense is, when your function dimension is more than 1, like say 3, people would say that, oh no, Harry, we cannot computationally too hard. We cannot really find the optimal transport, but actually you could. And you may use this kind of approach. And what you need is to kind of find the velocity over here. And how do you find the velocity over here? And what is there? This is just a wrong regression. You could use, your wrong regression, use any approach. You could use neural net or whatever approach. If you use neural net, you may worry about computational, highly non-convex, those kind of things. But in practice, they are doing well, doing very fast. So, and you may get a velocity, you may get an estimate of velocity, you may get the gradient, and then and you may eventually do some kind of iterative algorithm to get the upper transport. But this is an approach a computer scientist would propose, and then when you have infinite sample, then you have the distribution of x0 and x1, right? But as a statistician, I do not have infinite sample, and that means I have to estimate the distribution of x0 and x1. So if I estimate distribution of x0, okay, and I could use the approach what we did before, right? And under the Watson distance, I could estimate distribution of x1 and under the Watson distance, right? If my density is in the hollow ball, I could estimate optimally under the Watson distance. And another way to do it, you could run the ODE instead of SD, and you could calculate the velocity, and the velocity is amazing. It's completely determined by score. And the score, we have already talked about it, how to estimate it, right? And it's kind of amazing. So, and if you run a regular flow, and you could also get rate optimal estimation of the distribution and of x0 and x1, and as well as you could estimate more optimally. So, and then if we suppose we have the distribution of x0, you know how to generate data there. If you know how to generate data there, and then you could just run iterative C regular flow and to get optimal to get an estimate of optimal transport. And by using some kind of stability result, you could show that and your estimate of optimal transport is optimal. Is that amazing? So you could estimate optimal transport optimally. Okay, so of course it's under very specific function class. And then a natural question you may ask, and what other representation we should use, and so that we could do well. And recently, Larry Wasserman and the same year and his co-authors and wrote a paper of more than 100 pages just to make sure the ODE would have a good solution. You have some kind of existence and uniqueness of the ODE. And my student and I have been working very hard to understand how fast the algorithm converges, because it's an iterative algorithm, and so far the best result would prove it is converges very slowly. In practice, a few iterations would be enough, and we believe and the error will converge exponentially fast, but we are not there yet. For some concrete simple examples, we could prove it converges could converge exponentially fast. So, okay, that's the optimal transport estimation. And now I guess I have to end the talk. Is okay, we talked about, we introduced the diffusion approach to do sampling. We talked about optimal score estimation, and we believe optimal score estimation will lead to optimal sampling. And for whole smooth class, we prove that this is indeed true. For general class, we're not there yet. And Watson distance is related to optimal transport, and we also show that, and you may do estimate optimal transport optimally, and if you could get good estimator under the Watson distance. Thank you. That's all I have to say.